Margulis lemma because we need the parameter there, so the Margulis lemma. Or even before, we assume that no, actually, okay. The Margulis lemma given given n, there are m and epsilon, so n is the dimension. So m is an integer and epsilon is a positive constant, such that if x is let's say Hadamard manifold, with bounded curvature, and gamma in the isometry group is discrete, and x is a point, then gamma x epsilon, which is the group generated by all gamma in gamma, such that the displacement at x is less than epsilon, has a normal important subgroup of index at most. So this is a Hadamard space of dimension n. So that's m and epsilon depend on the dimension. And you can also, if you want, maybe later you can also bound it in potency degree, but so far we don't. Today we will not need that, but we will need this m and epsilon. So from now on, epsilon is this epsilon, and m is this m. And let me recall some definition from last week. An isometry. Gamma is called M stable if mean gamma, the set where gamma extends the minimal displacement, equals mean gamma to the I for all I which is at most n. That's what. So the minimal set can increase when you take power a priori. It cannot decrease, but it's always a totally geodesic submanifold. So the dimension is bounded, and so it can increase finitely many times. So you can always replace gamma by some power such that you cannot never increase, but this power will be large. But if you only want that it will not increase for small powers, then there is this lemma that we had from last week. Maybe I gave it as an exercise. There exists m. M is not good, but let's say there exists a m star. It's an integer depending on m, such that for every gamma in the isometry group of x, there exists I, or I which is at most m star, such that gamma to the I is m stable. I can replace gamma by some bounded power which become maybe not totally stable, but m stable. So m this M star depends on M. And we denote, and if I is the minimal one, for the minimal I, such I, we denote we denote by gamma star to be gamma to the I. So gamma star is a small or bounded power of gamma, and it's M stable. So I can replace every element by a bounded power which is M stable. That's what is given by this lemma. And maybe I want to say one thing is that the displacement of gamma star at any point x is at most M star, the displacement, or right, it's most M star, the displacement of gamma. You see that. Because gamma star is a gamma to the I, where I is at most M star. So, okay, this is to have in mind, keep in mind. And okay. So again, the goal is to bound the complexity of a manifold if we only know a bound on its volume. So how the volume control the complexity, and the idea is to decompose the manifold to a thick and thin part, and to control each of them. But the better idea is to find to bound the complexity of the thick part, and to show that if we remove a small set from the thin part, from the space itself, then there is a deformation retract. So okay, so let's recall some definition. So first, so again, let M be an X manifold, so it's X mod gamma, an X manifold, and gamma is the group of text of function, it's the fundamental group of M. This is and now I define the stable, let's say the stable singular, the M stable singular subset of X. I denote it by N tilde. It will be the union of all minimum of gamma over all gamma which is not 1, M stable, and such that the norm, the spectrality of gamma is less than M. Whenever, if you want, I remove all short stable geodesic, if you want. But it's not just geodesic, it's the minimal set of stable elements which has small displacement. Rho gamma is I remind you, Rho gamma was the infimum of D gamma. So if you want, if gamma is parabolic, then this set is empty, but if gamma is hyperbolic, this is some totally geodesic submanifold. It's a union of all the excess of gamma. And this is the stable singular subset, and I denote by N to be the quotient of N tilde, or if you want, it's N tilde divided by gamma. So N tilde is gamma invariant, and I can divide it. Or if you want, N tilde is gamma precisely invariant. It's not a connected set, but no, it's a gamma invariant. But it's not a connected set. But the quotient is also not connected necessarily. But this is the N tilde. And then there are two results. Okay. Now I define the stable thick part. epsilon stable epsilon, the m epsilon, or let's just call it the stable thick part.
Sorry, pi is the covering knot.
Huh?
Pi is the covering knot from m tilde.
What?
Pi is from m tilde to m.
Yeah, pi is the, yes.
Yeah.
This is the projection, the covering knot. Yes, this is the map from X to Y. And the thick part, or the m epsilon stable thick part, m epsilon stable thick part, I define it by, let's say, m bigger than epsilon star. Let's first define it by tilde. Is to be is the or let's define the thin part first. The m epsilon stable thin part is the union of all t gamma less than epsilon such that gamma is not 1 and gamma is m stable. By the way, if gamma is parabolic element, so automatically it's stable. For parabolic element, the minimal set is empty, so it's automatically stable. But for hyperbolic, I may replace every element by some power. But okay, this is the stable thin part. If you want, okay, and then I defined the stable thick part to be the complement. We define, so this is less than epsilon, and the stable thick part is star is just the complement, x minus m less than epsilon, and the quotient of it to m, again it's a gamma invariant set, and I can project it to m, and the stable thick part would be the stable thick part would be m bigger than epsilon. This would be just the quotient by gamma of m. That's the stable thick part. M epsilon. Any problem here?
No.
Okay, and then here is what I am going to prove today. I only know, okay, so far I know it. I'm quite sure it works in general, but so far I know in detail the proof only for M compact. So no, there are two theorems. Theorem 1.
M and epsilon are independent. Can
What?
we change epsilon according to m?
The little m and epsilon. Epsilon and m are the Margulis constants. They are given by the Margulis lemma, and sometimes people care what is the largest epsilon, which is best for a given dimension. So of course, if we take smaller epsilon, it will work as well, and if you take bigger m, it will work as well. If you remember in the proof that I gave, we choose first m, and then we took epsilon to be 1 over m. But it was just a matter of the proof.
So they're not different.
Yeah, there is the best m and the best epsilon, but
And the best epsilon for a given m, right?
no, well,
That's my question.
yeah, and you say, can you get a better m? So m is M you can control independently of epsilon somehow, because there are theorem like Jordan theorem, that if you have a finite subgroup of GLN, then it has subgroup of bounded index which is a billion. And there are similar theorem if you have a solvable subgroup or virtually solvable or virtually important group, a discrete group in GLN, then you can also bound the virtual the index. So you can bound it independently of epsilon. You can bound M. But
you can get different optimal epsilons for different M's, right? Or did you say that no?
I don't think. So we can think through it, and in fact, there are some tasks people would like to know what is the best epsilon for a given dimension, even in the hyperbolic case. And I think there are estimates, but nobody knows the optimal epsilon. So that was the interest of various people. They studied the various papers in the literature that study the Margulis constant, the epsilon. M is a different. There are other papers from other people who don't really care about usually about Margulis lemma. There are more algebraic paper which study the virtual index, the M, in more general settings like virtually solvable subgroup of GLN. What can you say about the index? So there are results about this. It's not very geometric. It's more algebraic group. But okay. But for us, okay, we fix the epsilon and M, and you will see that we are not very economic with the constant later on. We will wait. So in fact, all the results that we obtain about homotopy type, about the homotopy type, it turns out that some people from other fields, from K-theory and other fields, cares about the precise estimate, like the precise constant, not just the asymptotic that it's linear with the volume, but they care about the precise. And the proof that we give here is not economic, so maybe it's not good for them. So if one of you likes this mathematics and wants to go into the proofs and improve constant, there are work to do. So okay, so the first theorem is that there is a deformation retract from M minus N, call it N, yeah, from N minus N to M to the stable C.
So last week you did that without the star.
Yeah,
Is it not true, or you just
no,
did
it's true. The formation of type is true like I did last week and like I do before, but the next theorem I don't know without the star.
Oh.
So this theorem, the star doesn't matter for this theorem so much. You can play with it. And the second theorem, theorem 2, and I think it's true without the assumption, but if M is compact, so it's not important, this assumption, but so far I know it under this assumption. Then the epsilon thick part, stable thick part, is homotopy equivalent to d alpha v simplicial complex. D alpha, this V is the volume. Simplicial complex where D and alpha depends only on the dimension. So again, in the symmetric space case, I know this theorem without the compactness assumption, and actually I knew it before. First I knew it for the non-compact case and then for the compact, but in the general Hadamard situation, I still, so only yesterday I figured out the last details in the case that M is compact. And this is what I will, so today I want to explain you these two theorems. Basically, the first theorem we did a good preparation for it last week, and and the second. So okay, now we will do that. But you see, there are many applications because look at this. M minus n. I throw out for m something small, and sometimes you can control this n. For instance, if m is negative curvature, n is one-dimensional. If you throw a one-dimensional submanifold, so actually a bunch of circles, from a manifold, you keep a lot of the structure. For instance, you don't change the fundamental group. If the dimension of m is 4 or more, in dimension 3 you do change the fundamental group, but in dimension 2 you can actually destroy connectivity. In dimension 3 you don't destroy connectivity, but you may add relation to the fundamental group when you may change the fundamental group, you add or subtract it. But in dimension 4 you don't change the fundamental group. If you throw out a circle from 4-dimensional manifold, the fundamental group stays the same. And if it's higher dimension, so you don't change also the higher homotopy group. So it's still, this is very similar to M, and also in the, not just in the negative curvature, in many other situations you can control the dimension of it. And you know that you don't change the fundamental group. And then you have a deformation retract to this, and this you understand completely. So it's these two theorems together are quite strong. And so let me start by reviewing the proof and completing the proof of first theorem, and then we go into the second theorem. And okay, we have 2 more meetings this semester, and I hope that by the last meeting I will know how to remove this assumption. I will explain why I saw it at the moment. So what was the idea of the deformation retract? We had the following lemma. Recall that we had the following lemma from last week. Let delta be a group, finitely generated group, be a virtually nilpotent group, of isometries X, and exactly let's say M virtually, and let X be a point in X, then there is a direction at the tangent to X such that for any I such that, it's a bit complicated, such that X is not in the minimal set of gamma I to any power, J for J M, is that, I think this is more or less what we put. Then the gradient of d gamma I at X is not 0. This is more or less, maybe we had a slightly different assumption here, but the same argument showed this. This is what I mean today. And
So this is
May-
the same as saying that it's not in the minimal set of gamma star, gamma I star.
Maybe I formulated a bit later, a bit different last week, but the same proof shows that. So let me now formulate it this way. It's the same, more or less the same lemma, and I didn't know last week exactly what will I use for the decomposition, but so this is the lemma, and then from this lemma we had the deformation retract. Okay. So in particular, corollary for the theorem for any x which is in x minus n tilde, there is n hat tangent to x such that the gradient of d gamma times n hat is positive for any gamma which is m stable and d gamma of x is less than epsilon. This is the cover. If I look at x, I look at all the gamma which are stable and the displacement at x is less than epsilon. They form they generate a virtual nilpotent group, which the index of the nilpotent group is at most n.
So all gammas are in a discrete group.
In the lemma, we didn't need discrete
But
group.
here all the gammas are in a discrete group.
Here is a discrete group because here we are in the condition of the theorem. So yeah, and yeah, there is a discrete group gamma, and here I can define delta to be the group generated by all gamma, such that gamma is m stable and d gamma of x is less than epsilon. So there are finitely many of them. It's a group like this in the satisfy the same condition, and you see that. So this is the application. This is what we have. And the minimal set of each of them is inside n tilde, so we are fine. So if x is not in n tilde, then we are in a good situation. So how do we use this to define a deformation retract? Okay, so here there is another theorem that I will use, but okay, I will use something that I will prove later. But okay, so far we're fine. We had this recall from last week. We had this function, the real value function f. Recall that we had the function f from 0 infinity to 0 infinity, which was this function. This is the graph of it. It's always decreasing, it's smooth, and it's like that. That's the best. So smooth, so you see infinity, decreasing. F prime is negative on 0 epsilon, and F is constant on epsilon infinity. We had this function, and then from this function we constructed the function psi from x minus n to r, and the function psi at the point x was the sum of f of d gamma of x over all gamma, which is not 1, and M stable. So this is, it looks like an infinite sum, but because gamma is a discrete group, it acts properly discontinuous. At any point x, there are only finitely many elements whose displacement is less than epsilon, and only those elements count, because when the displacement is bigger than epsilon, f will give you 0. So it's a finite, it's a locally finite sum. At any point, it's a finite sum. So it's well defined. And then the observation, the first observation is that the thick part, the stable thick part, is exactly the set where psi equals 0. You see that? That's exactly the stable thick part. And from the lemma before we have the corollary from before is that for any x in x minus n minus this set minus the thick part okay, let's look at for any x in psi bigger than 0. That's a short way to write same set. What means psi 0? Psi equals 0 is the thick part. Psi bigger than 0 is what? Is x minus n. This is the domain of psi minus the thick part. So for any x there, the gradient of psi is non-zero. It's actually negative. What do I mean negative? The gradient is non-zero. It's a vector. It's not zero. The gradient is non-zero. And why is that? Because the directional derivative at the direction of n is not zero. The directional derivative will be negative, which is in the direction of n, and therefore the gradient is not zero. Okay, should I write it? Or? Okay. Now we can use Morse lemma. So the fundamental lemma of Morse theory. Morse theory is a beautiful tool. By topology, differential geometry. There is I recommend very much the book by Milnor. Are you aware of the book? There is a book by Milnor. It's called Morse Theory. If you have a month that you don't know what to do with yourself, take this book and read it from. It will make your month very joyful. It's a beautiful theory, and it's a beautiful book by Milnor, who is the best writer I think in the world. The problem with reading Milnor's is
What is the name of the book?
I think the name of the book is just Morse Theory. The problem with Milnor, with all the books that I read of Milnor, that he's writing too good. So it's like reading Winnie the Pooh. I mean, you don't need to struggle. You just everything is clear. You just think you understand everything, and then you put the book aside, and suddenly you cannot reconstruct the argument. So you need to make it harder for yourself and see that you can prove everything in your own words, because is writing too well everything. And but the fundamental lemma of most theory that I'm going to use here is the following. So is the following. So let's say let M be a manifold. The smooth manifold. Smooth manifold, and let call it by a different name. Let phi from M to R be a function, and let A and B be two elements in R. A less than B, together, and and suppose that phi less than B and phi less than A are both compact. In fact, if it's enough to say that this is compact, this is a closed subset. And further, suppose that the gradient of phi is non-zero on the interval on this. Then there is a deformation retract from one level set to another. Okay, I will not give the proof of this, but this is not a hard lemma. It's the fundamental lemma of most theory. Basically, what is the fundamental deformation retract is it's given by the flow of the gradient flow of phi. So if you if phi is the gradient of phi gives you a vector field, and you use
Wait, so what do you mean by the gradient flow?
so the gradient at any point gives you a vector, and this collection of vectors gives you a smooth vector field. So phi is a smooth map. Let's phi be smooth map. C2 at least. Let's say C infinity. Yeah. C infinity. I think it's enough C2. But the gradient here, it gives you a vector field, and just the flow along the lines, the integral curve of the vector field give you a deformation retract from level set to level set. It's very intuitive, and since everything is compact, then the gradient will be bounded from below and from above, and you can solve the differential equation and define the integral curve. And this is there is nothing very hard behind this lemma. So this is I think it's called most lemma. And we want to use it. What is the problem? Why can't we directly use it? Because of that. We want the gradient of a function to be non-zero also on the A level set. We want the deformation retract from this to this, but we want for that to use this lemma, we need the gradient to be non-zero also on the A level set. For us, what is the A level set? Okay, let's first say a corollary. Corollary if the condition holds for AB, for A and any B, then there is a deformation retract from phi less than infinity to phi less than equal to A. Right? If you know to deform your space from less than B to less than A for any B, then you can do it from less than infinity to just this is obvious. I mean, it gives you a rule how to retract any x. So it's
So phi smaller than infinity is just the manifold, right?
Okay, the function does not have to be defined everywhere, right? From a domain inside a manifold. I wrote it on a manifold, but
it doesn't need to be defined
okay,
on a
yeah, it's a
submanifold?
manifold. Yeah, it's a manifold. It's a manifold, but in our case, the manifold is x minus n tilde.
Okay.
It's still a manifold. X
still a
minus n tilde
manifold?
is a differentiable manifold. Because n tilde is a total regular submanifold. Suppose you draw a line from a manifold, it's an open subset of a manifold, it's still a manifold.
But with too many lines.
Yeah, but it's still an open subset of a manifold, it's still a
Right,
manifold. So I shouldn't call it M, but maybe Y.
I call it
Or X minus N in that case. But that's not a problem. You can deform everything to that. But what is that? Okay. So let's apply this in our situation.
This is what you need.
What?
Don't you need the manifold to be compact? No? If minus infinity will be compact.
If the condition holds for any B, then in particular for any B, this set will be compact, and but then the union of them maybe not compact, but you can still define it retract. But so what's happened in our case? So what's happened in our case? In our situation, we had this function psi, which is the sum of f of d gamma x on the stable elements, and but so what do we know? We know that psi less than b. So claim first psi less than b is compact for any b. Why? Because what do I mean by psi less than b? I claim that. How do you show that? So for any b, actually for any b, there is, let's say, delta such that the injectivity radius such that for x such that if psi of x is less than b, then d gamma of x is at least delta for any gamma stable. Is that wrong? Psi, what do you need? What do you want? Sorry, I want, yeah. Psi, so psi, yeah. If psi is less than b, then in particular f of d gamma should be less than b for every d gamma. So you see that d gamma cannot be too small. Okay, so if you want the injectivity radius on this set is bigger than delta, or the stable injectivity radius is bigger than delta. This implies the stable injectivity radius is less than delta, which implies that the injectivity radius is at least delta over m star. Because the remark I said it after defining m star is that for any element, if the displacement is smaller than this, then I take its stable power, and the displacement of that will be less than that. So it means that we are in some thick part. We are in the delta over m star thick part, and therefore we are compact. So any such sub-level set is compact, then this is fine. So the consequence is the following. For every B, for every A, there is a deformation attack from psi less than infinity, which is, if you remember, it's x minus n tilde, to psi less than a, which is, but I want it to a equals 0. You can, and this does not follow from Morse law. And you can ask yourself, why do we want it for a equals 0? What's wrong with that set? This is some neighborhood of and it's true that the injectivity radius is bounded below here, so it looks good enough. But on this set, I don't know how to control the boundary so much. That's why I want exactly 0. If I go to the 0, to the precise stable thick part, I will know to say something about the boundary, which I don't know yet. So this is why I need. To conclude the deformation retract, we will need to use the following fact, which was remarked to me by Shachar Carmeli. So it's the following fact, which I will prove later. The thick part, by the way, I constructed the formation retract on the universal cover, but everything will be everything is gamma invariant, so I can project it to M and we get the deformation retract on M. So you see the flow, the function psi, the gradient flow, everything will be gamma invariant, so I can do it on also on the quotient on M. So the fact is that the stable thick part, this is something I will prove. So this is the proposition. This is a manifold with boundary, a compact manifold with boundary, and it has a color neighborhood, and it has so color neighborhood is the foil. So you can imagine and this inside our space. This is here is the thin part, and this is the thick part. And the color neighborhood is a neighborhood such that the difference is homomorphic to a product of an open interval with the boundary of. So that's a color neighborhood. And once you have a color neighborhood, now I'll continue by hand waving because I'm not going to prove this now.
So color neighborhood is inside the manifold?
The color neighborhood is
the
inside the
color-
big manifold, the M. Yes, and it's what you can imagine. It's like the color of the color neighborhood of the head of the dog is the head. I mean, with the color.
And it deforms inside M?
What?
And it deforms inside M to the boundary?
Yes. But here this formation will not be smooth anymore. Only topological. The boundary is not so smooth anymore. But there is a color neighborhood, and I will prove that there is a color neighborhood using the understanding that we have on the stable figure. So, in fact, I don't know. I'm sure it's true, but I don't know how to prove that the standard thick part, without moving to stable, is a manifold with boundary. No, actually, I know to prove. No. But it's more complicated. And for the stable manifold, we will see that it's a manifold with boundary, and it has a color neighborhood. And okay, so using this consequence, we can deform using Morse theory the full space x minus n to a small neighborhood of the thick part, and the small neighborhood will fall inside the color neighborhood. And then we can continue deforming using the deformation retract of the color neighborhood. So if you do two steps deformation retract, first using this Morse theory to this for small a, and then continue like that, you will get a deformation retract to the thick part. You can ask yourself why, if I can deform for any a, for any small a, why can't I just do it for smaller and smaller a and continue? It's always the same deformation using a gradient flow. But maybe when you do that using this, points which are very close will start to go apart, and in the limit it will not be continuous. So I have to do it until I'm falling inside a color neighborhood, and then to continue with the color neighborhood deformation, which is I will postpone the proof of that to later. Now we'll take a break, and after the break I will discuss theorem 2, which is actually the new thing I learned yesterday, how to prove theorem 2. So I want to discuss it.